All right, so we ended class looking at how to work the hypothesis testing steps for between groups ANOVA, and then we ran out of time. So this will be the rest of the lecture for chapter 12 for ANOVAs, including working an example. We kind of had already started about people's ratings of health snacks. So the steps are the same as the previous independent T, dependent T, but what we have to do now is modify that for ANOVA. And when we had started here, I just kind of backed up to this step just so you get the whole thing at once. So the assumptions for ANOVA are not really that different from independent T. So what is the DV scale? Right. And so remembering that the example is about ratings of health snacks. Oh goodness, can't get the right size here. There we go. And so they're rating everything from 1 to 10, so yes, it's an interval scale. Okay, because there's no 0. Then you have to ask yourself, is it normal? And we have 30 people finally, so yay, it is. Then the next question is random selection? Probably not, because they just had people at this luncheon, so they were a convenience sample, but I could randomly assign. It doesn't say if they did that, but you could. And the last piece is homogeneity, and we don't know yet. So look at the standard deviations or the variances, and we'll come back to this question. So for step 2, what I'm going to do is take the research and the null and write down every single group. So I've got cheese, candy, fruit, cheese, candy, not shandy, fruit. And the way this works is that it's always one-tailed because everything in the formula is squared, but it's not one-tailed, like I can't have a negative number. And so really what's happened is we've taken both tails from the t distribution and folded it in half. So we're just going to use an equal to and not equal to test for a lot of reasons, but mainly because we literally cannot get negative numbers. And so it might be that we expect the scores to go down, but you can't have a negative number. And so it's much easier to just assume that everything is equal and not equal. And so it also remember that t has been squared. So everything's folded in half. So the positive ends and the negative ends are the same now. So we're just going to, this makes it a little easier because there aren't any choices here. It's equal to, I'm sorry, not equal to here and equal to here. Now, the nice thing about this particular issue is that it allows you to just remember one rule, so it's equal to and not equal to. But I always think about ANOVA as sort of like an investigation. So, in a sense, the overall question for ANOVA, or sometimes called the omnibus test, which is the F test, what we're doing right now, is did something happen? So ANOVA, the purpose of ANOVA is to figure out if something overall happened. In a t-test, the question is, did something happen? But you might predict, did it go down, did it go up? But with ANOVA, since you have so many means, it's too complicated to say, I expect this one to go down, and this one to go up, and this one to go down. So it's much easier to say, did something happen anywhere? And then the next step you'll do, which is Posthoc test, which we'll get to here in a minute, is where did that happen? So it's sort of like, did something happen? Okay, now what happened? So step 2 is kind of easy. Step 3 is where we're going to write down all these different numbers, but especially the means. So I need to have those means and the standard deviations really to know what we're comparing. So to get a picture of the data, let's calculate the means. Okay. So let's do that first. Step 2, calculate the means. Make this a little bigger. So I'm going to do summary of my data set, which I have already imported here. It's chapter 12. And I can just cut and paste this. Oop, wrong window. So here are my means. And it looks like cheese is the highest, candy is the lowest, and fruit is the next, is in the middle. Now, are fruit and cheese going to be different? Those means are kind of close together. I don't know. So we'll see. Now, for homogeneity, I need to have the standard deviations, or you can do variance, but I'm just going to calculate those standard deviations. Now you cannot do standard deviation of the data set because that gives you the standard deviation of like everything, pretending like they're all one big thing. So we're going to do standard deviation of each column separately. Oh, I spelled chapter wrong. So I've got 0.95, 0.95, clearly made up data. Okay, 1.1 or 1.20. Okay. And so I would say that's roughly equal. They're pretty close together. You don't really need to include it in this step, but you need to do it. The next thing we're going to do is calculate the source table. Okay. And we've actually already done that in this example, but I'm going to show you how to get it from the output. And it's going to take you longer to set this up than to actually run it. Okay. So I'm going to cut and paste my source table in here. I'm going to leave it the way it is, but I'll show you where each number comes from. Okay. All right, so let me go back to my notes here. So we got the means already, but to get the actual ANOVA table, we're going to have to restructure the data, add a participant number, and then run a function called easy ANOVA. And you're going to be like, this is not easy. It is easy ANOVA. It is an easy thing to do once you get the data in the right format. Okay. So to restructure the data, we're going to use the Reshape library. You probably have this installed already. Don't use Reshape 2. That's a totally different thing. So we're going to use Reshape. We did use Reshape when we made plots in ggplot, but that's been a while, so let me re-explain it. So spelling not my strong suit. There we go. So first thing I'm going to do is load that library, so Reshape. Don't forget, you can also over here under Packages, click on Reshape. And what's going on is the data right now is in a wide format. So each person, each one of these spots is a different person actually, but the independent variables are in separate columns, and we need one column for the IV and one column for the DV. So that's called long format. So we need to go from wide to long, which is the melt function. First thing you want to do is save the data. So long data, we're going to be melt, the name of the original data set, so chapter 12. And then the columns you want to change. So I'm going to do measured. Hello, come on, computer. Measured equals the C function to combine all these together. So I've got cheese, candy, fruit. So what that does is it takes everything here under measured. So this has to be spelled correctly. So it matches here. It matches over here to here. Takes everything in that measure column and melts it down into one column. So let's run that and look at what happens. You will get this using as blank as ID variables. That's fine. We left one of the things as blank because we didn't need it. So we'll click on long data here. So now I have variable, cheese, 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 candy, and then value. These column labels are not super lovely, but variables your IV, values your DV. So it just took this data and stacked them all together. So it's kind of like I cut and pasted it in Excel next to each other. So I've reshaped the data using Reshape, not Reshape 2, Reshape. The tricky part is Reshape 2 has a function called melt. It does not work quite the same way. Okay, so make sure it's just Reshape singular. We're going to add a participant number, so you can actually cut and paste this as long as you called yours long data. Oop, wrong window. So I'm going to take my long data, I'm adding a column called part no for participant number, and I'm counting 1 up to the number of columns, or number of rows in long data. I do that. If I click on long data again, now I have one called part number or participant number that just basically counts up to 30. So it just gives each person a unique code because you have to have that for this function to work. So let's run the actual ANOVA here. We're going to use the EZ library. This is just a reminder. Variable is your IV, value is your DV. So what Reshape is doing to the names of the columns. Now, for easy, oopies, let's try that again. I'm going to copy this and I'm going to talk about what each part does separately. The first thing you want to do is load easy. This is not a function you probably have on your computer yet, so you will want to install it. Mine's going to tell me it doesn't like that I haven't updated R, but that's okay. So the first thing we're going to have is easy ANOVA is the name of the function. Data equals, and then data set here. So I'm going to make this long data because that's the data I have that I'm using. DV equals, so put your DV in here. I've already told you it's value. Between, for between subjects groups. Remember, each person's in their own groups, like independent T, equals variable. So you have to tell it which column has the factor labels. So see how this over here says factor with 3 levels. So the DV needs to be the continuous one with all of the numbers from the experiment. Between needs to be the one that includes the labels. If you get those backwards, the output probably won't run. Okay. Within subject's ID is the participant number. And then leave these two alone. Type equals 3, so we get the same math as other computer programs. Return AOV equals true, so that you see more of the output that you need for the source table. So I'm going to run all of that all together. It's kind of long. You're going to get a bunch of output, and you will get this warning. Don't worry about that. That's fine. Okay, so this is the output we're going to look at. So I cut and pasted that here. So what I want to look at in all of this here really is, if I had to like insert a shape, this probably won't work because it always freaks out on my computer. But if I had to pick what was important, it would be this ANOVA table here. Can't believe that just ran, but cool. So yes, this ANOVA table. And then down here, I would do the same thing to look at these things. So if I wanted to fill in my table, let's see if we can put these side by side with here, my word table here. Whoop, too tiny. There we go. Where would I get everything? Okay. So DF in here is this DF column here. So I'm just going to relabel these DF in. Okay, so that's where I got 2 from. DFD is this column here. Okay, that's where 27 came from. You don't really need to fill in 29, but you can just add going down. F here is labeled where over here. So this is where F is. P is your P found for this experiment. This is in scientific notation. Hold on to GES. We're going to come back to what that is in a second. Ignore this Levine's output. And then it gives you sum of squares. So this is under sum of squares. Oops, sorry, caps. And then it says variable. Okay, so that's where 67.2 came from. Sum of squares residual. The rest of this one you would just have to add yourself. Okay, and then for mean square, you're going to have to divide yourself. Just so you can see where I got all the numbers from. Okay. And so that's where all those numbers would come from from this output. Okay. My numbers are slightly different because we rounded. That's why our numbers are slightly off. All right. So if you want to fill in one of these source tables, you can cut and paste the output you got from this section and then fill in where each one of these things goes. It doesn't give you to you in quite the prettiest format, but it does give it to you in a much easier format than other functions. All right, now for effect size, I'm missing a slide. What happened to my F slide? Ah, crap. Okay, so we're going to throw in a slide right here. I apparently decided not to calculate step 4 and 5. That's cool. Okay, so step 4 here would be calculate the F critical, right? So what is F critical? Well, what we want to do is come over here. So we've been using PT and QT, so it holds that we should use QF, right? And if you're never sure about some of these, you can always put a question mark in the front and run that, and it will pull up the help file over here. Now, I don't know how helpful this will be for you, but it is a legit function. So QF will give us the quantile of F. And what we want to do is put in P, just like we've been doing. So 0.05 for this example. Degrees of freedom 1, degrees of freedom 2. 227. Okay. We want lower tail equals false all the time. So that tells me that my cutoff score should be 3.35. So what I'm going to do is I'm going to copy this, put this in the notes. Oops. Let's try again. Okay. And so what you want to do, there's no dividing by 2 because this is always one-tailed. So this is degrees of freedom between, degrees of freedom within, lower tail equals false. So don't change the lower tail part. No dividing by 2 since always one-tailed. Right? So our score is 3.35. So we're going to put that here. And it will help, especially in this section, if you will copy just straight from R, so that if you just made a typo on the way that you typed something, like maybe you put 2 and 72 because you just flipped the numbers, we can give you partial credit. Step 5 we've actually already done. So let's throw a slide in here for that one. So we're going to use F from the source table. And that's it. So I have 31.11. And then for some reason my example is also wrong. This is a hot mess. I'm sorry. It's like perpetual Monday at the end of the semester, right? So let's throw in one more thing below. Below this time? Yeah, here we go. Where we have step 6. And step 6 is do I reject or not? And so I look and see if my F found is greater than my F critical here. Okay. And it is by a lot, so we would reject them null. So that's step 5. One more slide here. Step 6 is F found in step 5 greater than F critical in step 4. Okay. And if so, reject the null. If not, you're going to fail to reject. So don't say I accept the null. That's not one of the answers. It's reject the null or fail to reject the null. Now, this time effect size, we're going to use R squared. R squared is a little different than Cohen's-d. Cohen's-d is the difference between means, but we have more than one mean, or more than two means. So there's not really a good way to represent mean difference there. Just like that's why we have to run this fancy ANOVA thing, is because taking mean minus mean just doesn't make a whole lot of sense. So what we're going to use is R squared. It's also called eta squared sometimes, and that's the little curly N symbol, eta. But what the formula is SS between, so variance due to our IV divided by variance due overall. And so think about this. We talked about F being a ratio of good variance to bad variance. Well, R squared is a ratio of how much of the variance is good variance. So this is a proportion. It will only be from 0 to 1. So let me add that here. Only 0 to 1. It is a proportion. So it can't get, it can't be 2, 3, 4, just like colon C can be 2, 3, 4, and negative. So this is always positive. It's from 0 to 1. And it's just the amount of variance accounted for by the IV. So let me add that as well. Just stick it over here. Oops. Stop. Just let me add a stupid text box. PowerPoint hates me. Right there? Yeah. Amount of variance due to the IV out of the total. Okay, so that's what R squared stands for. All right, so how do I find that? Well, I could do SS between over SS total. So let me go back over here. So I could do 67.2 divided by 96.3. Or I could make this whole shebang easier on myself and use this generalized effect size column out here. And that is the same math. So this is 0.70. And it's just here on the end. That's why I said, hold on, we'll come back to this. So I'm just going to look there because that's much easier. So do 0.70. How do I know if that's big or small? Well, let me give you some rules. So just like we have colons D rules where that's 0.2, 0.5, and 0.8, we also have rules for R squared. It's 0.01, 0.06, 0.14. Sometimes people use slightly different numbers, but these are the ones that are in your book, so use those. So that is a huge effect size because it's made up data. So it's a very, very large effect, and we found a significant difference. But I guess the question is, where's this difference? And so this really gets into how is ANOVA really different from everything else. So at the end of this ANOVA table, you have this Bonferroni Posthoc stuff. So let me talk about what all of that is. So back to my notes here. With ANOVA, gracious, the point of ANOVA is that you are trying to see if there's an overall difference. So the F test is some kind called the omnibus test or the overall test, which means that I'm looking for a significant difference somewhere. So it could be that cheese is different than candy, cheese is different than fruit, but maybe candy and fruit aren't any different. It could be that cheese and fruit aren't any different. So it could be that they're all significantly different. So there's, we're not sure about the pattern. So all ANOVA tells you is if there is a difference. So that saves you that type 1 error problem. We started this like a week and a half ago. Type 1 error issue is like I can't run a whole bunch of t-tests because then I have inflated my chance of finding a result. So I was cheating. But what I can do now is I've run the ANOVA and it's significant. So now I can do what's called a post-hoc test to determine where. So ANOVA is kind of like the low pass filter. Did something happen? So you can think of this as like maybe your significant other is cheating on you. You think, okay, so did something happen? And you find out yes or no. And then you find out what happened. Okay. That's a really like kind of a negative example, but also this way like most police force works. Did something happen? Okay, what happened? And who did it? Okay. So we have to figure out where those differences are. So we're going to run a post hoc test. And as you'll see in a minute, post hoc tests are just independent t-tests for between subjects designs. And then we're also going to talk about post hoc corrections, very specifically Bonferroni. There are other types of post hoc corrections. There's a whole alphabet soup of them. The most common ones are Tukey and Reshape, but we're going to do Bonferroni. So kind of an important, like, stop for a second, let's take a note here. We're going to run, analyses-wise, a post hoc test. The test itself, the statistical test, is an independent T because that matches the type of research design. So between subjects ANOVA is between groups research, which means it's an independent T for post-hoc tests. And why even do these post-hoc tests? Well, if we had 3 groups before, now we need to break it down into what are called pairwise comparisons. And this is when I made the Noah's Ark joke. It's a 2 by 2. So I need to compare each mean to every other mean. And so I need only 2 at a time instead of 3. Okay. So when you do those 2 at a time tests, it's an independent T, and that's the post hoc test. Post hoc corrections are a fix for those tests to solve our type 1 error problem. People often conflate these two. Bonferroni is not a test, it's a correction on the test. So it's like you fixed the test because you realized it was wrong. So about the Bonferroni test, yes, so this is where some of the confusion comes in. It is a post hoc, you know what, let's even just change this word because this isn't even correct. It's a post hoc correction on a test that provides a more strict critical value for every comparison. So we've been talking about hypothesis testing being a race, where we look at, did our little Scooby-Doo van cross the finish line? Well, when you run multiple tests, it becomes easier and easier to cross the finish line. Because practice, basically. It's not practice, but that's the idea. So instead, what we do is we take the finish line and move it further out for all the tests. So we can't cheat so much. And Bonferroni is the easiest of these post hoc corrections. Because what it does is you figure out how many comparisons you're going to make. And so go back to the very beginning of the notes. Let me find the slide. It's like the second or third slide. Sorry, fourth or fifth slide. And it shows you here the number of means. This is slide 7. If I have 2 means, there's only 1 comparison, so there's no correction. That's independent T. If I have 3 means, there's 3 comparisons. 4 means there's 6 comparisons. So this will tell you how many comparisons there are. So we're here. Oh, I put it in again here. Sorry. So it's the slide right after this as well. So we figure out how many comparisons we're going to make. And then we're going to divide P by the number of comparisons. And so really actually what we're doing is dividing alpha, which is that like P less than 0.05, P less than 0.01 jazz, by the number of comparisons. And so this gives you an example. If there are 3 means, there are 3 comparisons, and we take P less than 0.05 and divide it by 3, so it's alpha divided by 3, and we get 0.017. So that's our new cutoff score, where P values have to be less than that, because think about it, if I have 3 tests, those add up to 0.05. So essentially I'm giving each test, so it's another Oprah moment, we're giving each test its own little mini space to find a rejecting of the null. Okay. And so we're saying like we're okay with 5% of saying the null is false when it's not. And we have 3 tests, so each of you get part of that. So we're dividing it up. Okay. So use this table if you have a question about Bonferroni in the multiple choice section. Okay. Click here. What we're going to do is run this in R, and it's the t.test code with a couple little modifications. Let me copy this. Remember, cutting and pasting quotes sometimes does not work. So first thing we have is the name of the data set, and then the DV, so value, okay, the name of the data set, and the IV. And I should back up a quick second. It says pairwise t.test. And so it's not just t.test, it's pairwise t.test, and we'll get into what that does in a second. Okay. Paired equals false here because this is an independent T. Var equals true. Remember, that's the homogeneity thing. And then this is new. So actually, this is all independent T here. Like if you pull up your code for chapter 11, that's the same code. Here's the new piece. P.adjust method. So this is the correction part. So see here, here's independent T. We're running independent T. Here's the correction. Okay, so they go together, but one is the test, the other is the fix. And then equals Bonferroni. 2 R's, 1 N. So the pairwise part is going to take all three means that we have and run them all against each other. And it makes a cute little table, so let's run this. And so this is a little table I'm talking about. Now one quick thing is if scientific notation is hard for you to read, you can do options, scipin equals 999. I have no idea, but that option will turn off scientific notation. Boink, 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 boink. And then you can see it maybe a little better without the crazy e to the -5th stuff. So this is the piece with scientific notation, and then I ran again without scientific notation. So what do I do with these numbers? What do they mean? What's going on? What I'm going to have you do is something I have my graduate students do, is fill out a little table that'll help you just clarify what is this thing. And so that's what's at the bottom here. So first thing you want to do is write each group compared to every other group. So let me try and see if I can put these next to each other. Okay, so we can kind of see. So group 1 here, I'm going to take cheese versus candy. And then I'm going to do cheese versus fruit. And then candy versus fruit. Okay. What the next thing, I want to add the means in, but I have this pulled up right here, so I'm going to look at it. So p-value is this number here. So it gives me p. So that's a big number, so I'm just going to put p less than 0.001. Thanks for capitalizing word, but you can cut and paste the literal number in there. Cheese to fruit is 0.046. Candy to fruit, also very small. 0.01. So this is found P. Okay, this is the P for the experiment. What I tell you to do first, actually, well, kind of too late for that. That ship has sailed. But is it gonna scroll? Okay, it scrolled through 3 slides. It's put in the means. So where did I get these means from? Well, that's that summary that we did up here. So 6.3, 2.7, 5.0, 5.1. And that's just going to help you in a minute figure out what the hell is going on. So I'm going to fill those in. So my mean equals 6.3. And that's true for both cheese comparisons. So everybody's going to be in here twice. My candy mean is 2.7. And then my fruit mean is 5.1. So I have my means, who's compared to who. And I figured that out by looking at this and just figuring out like where they intersected. So this is cheese and candy here. And then I have their p-values from the output. Now what do I want to compare to? So this is where, this is actually a note at the bottom of the example here. So if you were to run a Bonferroni manually, so this is actually more for your homework. If they ask you a question about they found a p-value of 0.043, what should they do? That sort of question. If you run that Posthoc test with no correction, so you don't use that line p.adjust method, you will take p found and compare that to p critical. Okay, so you take our p found value here and then compare that to alpha divided by the number of comparisons. Remember that alpha is 0.05 or 0.01, and you can pull those from the table. So we would take 0.05 divided by 3 is 0.017. Okay. We want P found to be less than P critical. Okay. So just as an example here, if this doesn't match the one above, just an example. If alpha is 0.05 and we had 5 comparisons, P critical would be 0.01, so 0.05 divided by 5. If our uncorrected t-test was 0.02, I would fail to reject because that is not less than 0.01 here. If our uncorrected was 0.005, I would reject. So this is more like a book question. If I'm using pairwise T and R, here's the great part about this. This is what I love about statistical programs doing the thinking for me. If I have pairwise T.test, it uses that p-adjust method. and it corrects the p-value for you. That's really important. That means that these numbers are corrected for the number of tests. They are different from uncorrected numbers. So just as an example here, if I ran this without that last line, okay, I'm going to have to close my parentheses here. Okay, those numbers are different. So the easiest one to look at is 0.015 versus 0.04. Okay. What Bonferroni does in R is it corrects these based on the number of tests. Okay. So it fixes these for you. What that means is that I can just use alpha from my problem as my comparison. That makes life so much easier. Ooh, what just happened? Because then I have to just remember one rule, p less than 0.05, and not, okay, how many tests do I have? Okay, what is the new p critical, and that kind of stuff. Okay. Most people like this method because it means they're always comparing to their alpha rather than trying to remember all kinds of new scores. Okay. So we define p less than 0.05 at the beginning, and we're going to stick with it. Okay. All right, so now we're going to compare a p-value to our comparison. So over here, so is p less than 0.01 less than 0.05? So yes. Okay. Is 0.046 less than 0.05? Just barely, but yes. And is 0.001 less than 0.05? Yes. But that's not quite enough. I've said, okay, all the pairwise tests are significant. And if you tell that to somebody, they go, and? They probably actually would be like, stop talking mumbly gibberish, but what does that mean, right? So now I'm going to look at my means. This is the part where we get into what happened. Okay. So I've got cheese has a greater score than candy. So people like cheese more than candy. Of course they do. People like cheese more than they like fruit. Go cheese! Okay. And then here, fruit is rated higher than candy. Okay. And so where I'm getting those numbers from is I'm literally just looking at the means. 6 is a bigger number than 2. So overall, cheese is rated higher than fruit, which is rated higher than candy. So if I had to rank the healthy choices selections, it would be cheese, then fruit, then candy. And so now I know what happened in my study. So we said the ANOVA was significant. Oh no, I forget how to fix this. Okay. Well, we'll come back to it. We said the ANOVA was significant. Now we figured out where the significant things were. They won't always be all different. But we figured out what happened. Okay. So my interpretation of what happened in the study was that cheese was greater than fruit, which was greater than candy because cheese is the best snack. And that is like the end of how all this stuff. So there weren't really confidence intervals. If you wanted to do confidence intervals, you could do them on the mean. But it does have this extra post-hoc test part. And so kind of a quick piece to end on. How did this solve my type 1 error problem? Right, we started by saying I can't do all pairwise t-tests because type 1. And then we ended with doing all pairwise t-tests. And people were like, what is the point of this? What we did was we did all the pairwise t-tests after discovering that there was a significant difference somewhere. So if there wasn't a significant difference somewhere, we would have stopped and never done this because the F test wasn't significant. So if I got here and I said fail to reject, I wouldn't keep going. I would stop and not do this part. And then the second solution to our type 1 error problem is that we ran this Bonferroni correction on our posthoc. So that helped fix these p-values so they weren't too small. It made them larger. So we started this whole section with ANOVA as a solution to type 1 error of running a whole bunch of tests at once. And that is how we solved the problem by adding an overall test to see if there's some difference somewhere, and by adding these posthocs with corrections to fix the type 1 error problem. So that is the end of chapter 12. More examples to be recorded next week.